Record on this computer. Okay, so we're starting to record. I don't think I'll really start the class until 5:30, but if somebody has a chat question, shoot it to me and or to us all, and I will try to answer it. I'm just wondering if I can move this thing. Ah, yes, I can. Oh, that's so nice. Okay. All right. So does anybody have any sort of question? That would, we've got another minute here. By the way, turn in your homework, however you do it, to the grader. And his email address is on the class webpage. The class webpage, of course, is quantum.phys.unm.edu/466-20. By the way, there's another issue that maybe one of you would have a good idea about, so I'll ask you guys and you can think about it and maybe send me email over the weekend or whatever. The question is how to get you the solutions to the homework problems without having those solutions appear all over the internet, which makes it hard to give them for anybody to use them in the future. So if somebody has a good idea about that, let me know. All right, I think we can start the class now. Let's go back to the consideration of a square matrix. And what we saw last time, in fact, we've seen this in several classes, is that a diagonal, if you have a square matrix, the eigenvalue equation looks like this, and we can rewrite it like that, and this is possible only if lambda is, of course, an eigenvalue, which means that the determinant of A minus lambda I vanishes. This is when the columns of A minus lambda I are linearly dependent, which also means that the rows are linearly dependent. And vanishing of this determinant, hello? Let's see, everybody's supposed to be muted. Anyway, the vanishing of this determinant is an equation that's called the characteristic equation of the matrix A. And MATLAB, by the way, can generate these characteristic equations. And maybe we can give more examples next Wednesday. For an n by n matrix, it's a polynomial of the nth degree in the unknown eigenvalue lambda. So it looks like this. The first term is the term corresponding to lambda equals 0. That's obviously just the determinant of A. The term of highest degree is minus lambda to the n, and that's this term. Turns out the term of next highest degree is proportional to the trace. And all of these coefficients of lambda are actually invariant, I should say, I guess, polynomials or examples, invariant functions of the matrix A. And this equation is, which is, as I said, the characteristic equation. It's sometimes written as P of lambda and A, and it's a sum of coefficients pk lambda to the k. All of these coefficients pk are basis independent, because if you change basis by letting A prime be S inverse AS, where S is an n by n matrix, arbitrarily complex, I see. Somebody just had a brilliant suggestion. Hold a Zoom session where I screen share the homework solutions. So I think that might actually make sense. We could do that in a Wednesday class following the deadline for turning in the homework. That's quite a good idea. Anyway, what we have here then is S inverse AS minus lambda. You can then rewrite it this way. You know determinants of products of matrices are products of the determinants. The determinant of S inverse cancels the determinant of S, so we're just back to the polynomial. So it's simply the characteristic polynomial is basis independent. And what we'll learn when we do complex variable theory is that any nth order polynomial equation has n roots or n solutions somewhere in the complex plane. Now, it could be that some of the roots overlap, in which case you might not have n different roots, but you always have n roots in this sense. So what we can say here is that every n by n matrix has n eigenvalues and n eigenvectors. And whether these are linearly independent is another matter. We'll get to that later today. The matrix whose columns are the eigenvectors of the matrix A is called the modal matrix. And that's one of the things that MATLAB returns when you do the when you use the eigen function. Consequently, acting on this modal matrix, which is a matrix whose columns are the eigenvectors of the matrix A, what we get is A turns each column into the A multiplies each column by its corresponding eigenvalue, and so it looks like this or equivalently like that. And this was the matrix equation that, this is why MATLAB writes the eigenvalues in a funny way. It writes it as a diagonal matrix. And so you then have AV is V times that diagonal matrix. If the eigenvectors are linearly independent, then the matrix V is non-singular, and then it has an inverse, and then we can multiply this equation from the left by the inverse, and we get that V inverse AV is the diagonal form of the matrix A. And so that's the statement that if you have a square matrix and the eigenvectors are linearly independent, then you can diagonalize it. So I'm going to be skipping all the examples today because we just need to get on with the other material. If we set lambda equal to 0 in the factored form, in other words, if you find the n roots of the characteristic equation, you can write the characteristic equation in this form. If you set lambda equal to 0, you see that P of 0A is just the product of the eigenvalues. And now in general, or as sometimes people say, except for a set of measures 0, the n roots usually are all different. And when they are, the eigenvectors are linearly independent. And we can show that by a proof here. I don't know how well proofs work in a Zoom session, but in any event, The first eigenvector is obviously linearly independent because it's said one eigenvector is always, one vector is always linearly independent unless it's the zero vector, which is, of course, you can't have a, when we are talking about eigenvectors, we assume that the eigenvector is not identically zero. That's a trivial solution and is excluded. Eigenvectors have to have a non-zero norm. Anyway, let's assume the first k less than n eigenvectors are linearly independent. We can then show that the first k plus 1 eigenvectors are linearly independent. If we assume the contrary, that they're linearly dependent, then there would be k plus 1 numbers CL, not all zero, such that you have this equation. We now multiply this from the left by A and use the fact that these vectors are eigenvectors of A, and so A turns them into themselves multiplied by the corresponding eigenvalue. If we multiply the same equation, namely this one, by the k plus first eigenvalue and subtract, what happens is the k plus first term in these two expressions cancels, and what we have is this expression here, and then all these numbers are different from zero because we assume the eigenvalues are all different, and but that would mean then that these vectors, these k vectors, are linearly dependent, but we assumed that they were linearly independent. So this tells us then that if all n eigenvectors of an n by n matrix have different eigenvalues, then they are linearly independent. And if any subset has different eigenvalues, then those ones are also linearly independent. And if the root of the characteristic equation lambda is just appears once, in other words, it doesn't appear as lambda minus lambda 1 squared or cubed, then that's called a simple eigenvalue. And one that occurs n times is said to be an n-fold degenerate eigenvalue would have algebraic multiplicity n. The geometric multiplicity is the number of linearly independent eigenvectors with eigenvalue lambda. And so if any eigenvalue of an n by n matrix has fewer than n linearly independent eigenvectors, we say that it's defective. So effectively, every non-defective square matrix has n linearly independent eigenvectors, and consequently, it can be diagonalized by a similarity transformation. So to repeat then, if you have a square matrix, you always have n eigenvalues and n eigenvectors. If those n eigenvectors are linearly dependent, then you can diagonalize the matrix and it's said to be non-defective. On the other hand, if it's defective, then you can't diagonalize it. Let's see, we have a few questions here, and one is a suggestion, put at mailbox. Let's see, could the person who sent me that good suggestion send me an email explaining it? I don't quite know what put it mailbox means. I should know what it means, but I don't know what it means. So just send me an email, you know, tonight or over the weekend. Another question, is there an advantage to working with? Yeah, clearly, if you have two vectors that are linearly dependent, then then they're proportional to each other, and you don't need both of them. Similarly, if you have three vectors that are linearly dependent, then you don't need all of them. Maybe two of them are linearly independent, two of the three linearly independent, and then so you only need to use those. Okay, so I've caught up with the chat and understand what mailbox meant. It was physical mailbox. I thought maybe it was a Zoom feature. All right, let's go on now. And incidentally, the trace of every non-defective matrix is the sum of its eigenvalues. And the determinant of a matrix is the product of the eigenvalues, and the determinant of every non-defective matrix can be written as an exponential of the trace of the log, and equivalently, the determinant of e to the log of e to the L is the exponential of the trace of the log. We can discuss this on Wednesday. And this example. Let me go on to the fact that a matrix obeys its characteristic equation. This is really important. The characteristic equation, of course, is of this form. It's just what you get when you form the determinant of A minus lambda times the identity element, and that's an nth order polynomial. And it remains true if you replace the matrix A. I'm sorry, when the matrix A replaces the variable. So in other words, it's P of AA. So it's this expression where lambda to the K is actually A to the K. And I think this is worth proving, especially since the proof is a very nice proof by Gelfand, who's a Russian mathematician who actually died not long ago, maybe 10 years ago. Anyway, to see why, what we do is we go back to the formula for the inverse of a matrix. And the inverse is the cofactor matrix times divided by the determinant. And if you rearrange that, you have this equation: A minus lambda I times the cofactor matrix is equal to the characteristic polynomial times the identity matrix. And the transpose of the matrix of cofactors is a polynomial in lambda with matrix coefficients. So these C's are actually matrices. And if we combine the last two equations with the characteristic equation, what we have is this: A minus lambda I times this is equal to P of lambda A, which is, well, just multiplying. It's A, C0, and so on and so forth. In other words, you take A minus lambda I and you multiply, you use it to multiply this right-hand side of this equation, you get that. And we already know that that is equal to the characteristic polynomial times the identity, which is to say this. I left out the identity. Maybe I should put it back in. Anyway, what you do now is you just equate equal powers of lambda on both sides of the equation. So the lowest power of lambda on this side is AC0. And so it has to be P0 times the identity. The highest power of lambda on the left-hand side is minus Cn minus 1. and the highest power of lambda over here is Pni, and then you can figure out that these are some of the intermediate ones. Now what you do is quite cute. You multiply the first equation by I, the second one by A, multiplying of course by both sides, and the last one by A to the n, and then you add up the left-hand sides and the right-hand sides. Well, the left-hand sides cancel exactly. And the right-hand sides, when you multiply this by, let's see, the first one by, you just multiply this by the identity, this by A squared, and sum, you've constructed the characteristic polynomial on the right-hand side. So this is just the statement that 0 is that the characteristic polynomial with lambda replaced by the matrix is a matrix equation that gives 0. And the various terms look like this. And so this is called the Kaylee-Hamilton theorem, or Kaylee-Hamilton theorem, I don't know how it's pronounced. And this derivation, as I said, is due to L. Gelfand, who died 11 years ago, actually. He spent most of his life in the Soviet Union, but immigrated to New Jersey at sometime probably during the Gorbachev period, or Gorbachev period. Anyway, because an n by n matrix obeys its characteristic equation, this nth power can be expressed, can be determined, can be written in terms of the lower powers of the matrix. For example, the square of any 2 by 2 matrix can be written as minus the determinant times the identity plus the trace times the matrix. And there's an example of that that's quite useful, actually. Let me go on now to functions of matrices, which is something that we touched upon in a question during one of the Zoom classes earlier, one of your earlier Zoom classes. Suppose you have a function, and of course here I'm talking about a well-behaved function, f of x, which has a power series expansion, same. So how do you express this as a function of the matrices? What is f of a? If f is that, what is f of a? Well, you can use the previous theorem, namely that you can start by writing C0 times the identity plus C1 times a plus C2 times a squared and so forth. But then when you get to a to the n plus 1, or even a to the n, you use this relation to express a to the n in terms of the lower powers. And so what you can do is you can write f of a always as a polynomial of the first n powers of the matrix A, starting with 0 and going up to n minus 1. So that's a useful thing to do for n equals 2, and it's a possible thing to do for n equals 3, but beyond that, it's a kind of nightmare. On the other hand, if A is a non-defective square matrix, then you can diagonalize it, and you can define the function of the matrix A as the diagonalizing, as the modal matrix times f times a matrix which has the function, which has f of the first eigenvalue of the matrix A times the inverse of the modal matrix. So it looks like this. If the little a's are the eigenvalues of the matrix A, then it's f of A1, f of A2, f of AN. And that's what f of AD is that goes in here. This is then a matrix, and we can then write f of a as ck a to the k, of course, but now a to the k we write this way. And since V inverse V is 1, if we have V diagonal matrix V inverse to the K, all these other, a lot of VV inverses cancel, and we just have V, A, the diagonal matrix form of A raised to the kth power, V inverse. And that then is just V f of AD, which is this expression, times V inverse. So this is a very compact, very nice equation. And this is how we understand functions of matrices or functions of operators in quantum mechanics. Okay, so I'm going to skip these various examples, although if we should possibly run out of material this afternoon, then I'll come back and do one of them, especially if somebody wants to see a particular one of these examples. Anyway, Hermitian matrices play a big role in quantum mechanics, as you know. They have very nice properties. By definition, a Hermitian matrix is square, and it's unchanged by Hermitian conjugation or equivalently by complex conjugate. You take the complex conjugate and the transpose of the matrix, and there's no change. Since it's square, we know that it has an n by n Hermitian matrix has n eigenvectors, n eigenvalues. And what we can see is that all the eigenvalues are real. Of course, this is why you represent physical observables or real observables by Hermitian matrices or Hermitian operators. If you take the adjoint of this equation, you get k a dagger is a star k, but a dagger is a, and so this equation really is ka is a star k. You now take the inner product with k, and you get k, which is a k, kk equals a star kk. And kk has to be positive. Remember, I said that an eigenvector doesn't count if it's all zeros. And so you divide by kk, and you see that a k star is equal to a k. Now, since a dagger is A, the matrix elements of A between two of its eigenvalues satisfy this relation. And if we go through this, this is A star sub m, mk. Well, this is just, by definition, it's that. And on the other hand, we can rewrite it as this because A on m is am. And then this thing we know is just m a dagger k. But if A is Hermitian, that's MAK, and then A on K is AK. So now we have the result that A star MK is equal to A KMK, and that's this equation. But we already know all the eigenvalues are real, so this is the equation that we have. And now this tells us that if this is non-zero, they're orthogonal. And so this tells us that when the eigenvalues are different, the eigenvectors are orthogonal. Now, in the absence of a symmetry, all the eigenvalues usually are different. And this is why degeneracy occurs almost never if we're just talking about arbitrary matrices. It occurs often in physics problems because we study, especially when doing quantum mechanics, we study systems with a great deal of symmetry, and with a great deal of symmetry, some of the eigenvalues are equal, and so we have this degeneracy issue. If two or more eigenvectors have the same eigenvalue, we say that the eigenvalues are degenerate. In this case, any linear combination of the corresponding eigenvectors is an eigenvector of the Hermitian operator A with the same real eigenvalue. And then what you can do is you can use Gram-Schmidt to make these things orthogonal, and then we can normalize these mutually orthogonal eigenvectors. And so that's how we proceed. Now, we can consider two related questions. Are the degenerate eigenvectors linearly independent? And if so, what orthonormal linear combinations of them should we use for a given physical problem? Well, if we look at the first question, the second question first, we know that unitary transformations preserve the orthonormality of a basis. And let's see, I think I can make this screen bigger and it'll be easier to see and somewhat clearer. Anyway, so let's consider any unitary transformation that commutes with the operator A, and that then we say represents a symmetry of the matrix A, and it maps each set of orthonormal degenerate eigenvectors of A into another set of orthonormal degenerate eigenvectors of A with the same eigenvalue because A and U commute. So there's a huge spectrum of choices for the orthonormal degenerate eigenvectors of A with the same eigenvalue. What's the right set of for a given physical problem? Well, a sensible way to deal with that is to say, well, let's find another Hermitian matrix B and multiply it by epsilon. And so now we consider a slightly different matrix A, and we choose B so that it completely breaks whatever symmetry led to the degeneracy of the eigenvalues of A. And what you want to do, of course, is choose as the matrix B one that represents, well, it's also Hermitian and that represents a relevant physical observable. And so what one does in the case of angular momentum, where the symmetry is the symmetry of the rotation group, and the matrix A might be L squared or J squared if you have spin also, then the traditional thing is to choose the Z component of orbital or total angular momentum as the operator B, and that breaks the symmetry because rotations rotate the Z component of angular momentum into the linear combination, the X, Y, and Z components. So then what you have is this matrix A of epsilon will have n different eigenvalues and n orthonormal non-degenerate eigenvectors because you will have broken the symmetry because all these eigenvalues will be different. And then what you do is you choose the eigenvectors to be the ones that remain when you take the limit epsilon going to 0. If we go back to the original, the first question, we can show by a different argument that the an n by n Hermitian matrix has n orthogonal eigenvectors, and this is a somewhat abstract proof. The idea is that we first consider a space that's the space of vectors y that's orthogonal to a particular eigenvector k of a Hermitian operator A. So k is an eigenvector of A, and what we notice is that this space is invariant under the action of A. That is to say, K on Y, if that's 0, then K on AY is, of course, AK, KY. And so if KY is 0, so is KAY. So if vector Y is in a space of vectors orthogonal to an eigenvector of a Hermitian operator A, then the vector AY also is in the same vector space of orthogonal vectors. And what we say is that this space is invariant under the action of A. And so we represent we imagine we have A acting on an n-dimensional vector space S. It's represented by an n by n Hermitian matrix. It has at least one eigenvector. The subspace consisting of all eigenvectors orthogonal to it is an n minus one dimensional vector space that's invariant on the action of A. On this space, A is represented by an n minus 1 by n minus 1 Hermitian matrix. It has at least one eigenvector. The subspace orthogonal to it consists of vectors orthogonal to it and the other one, and we call that Sn minus 2 and so forth. And continuing in this way, we see that A has n orthogonal eigenvectors. And so we have the conclusion that Hermitian matrices are non-defective. What we do traditionally is we take the n orthogonal eigenvectors of a Hermitian operator A and write the identity operator that way, and then we multiply from the left by A, and we get A is equal to AI is equal to AI on the sum of the outer products of the eigenvectors, and that's the eigenvalue times the outer product of the individual eigenvectors. And this is the diagonal form of the matrix, of the Hermitian matrix A. And so this is expressing the operator that represents the physical variable, a physical variable, whatever A represents, in terms of the possible values of the physical variable multiplied by the outer products of the vectors that represent systems that have that positive eigen value, of that possible value of the physical operator. Schwinger years ago made a connection between this equation and actual experiments, and it's probably a paper worth reading. I don't remember what the reference is offhand. It was way back in, oh God, I don't know, the 50s or 60s of the last century. So I guess his view was the expansion of A as a sum of outer products of eigenstates exhibits the possible values of a physical proper representative A when selected non-destructive measurements represented this way of the quantity A are made. Exhibit, by the way, is a verb he used a lot. Anyway, a Hermitian matrix is diagonal in the basis of its eigenstates. In other words, if we have the linear operator A and we take the matrix element with its eigenvectors, what we get is an eigenvalue times the Kronecker delta. But in any other matrix, in any other basis, it looks like this. AKL would look like this, and this would be a these are the matrix elements of a unitary operator. These are the matrix elements of the adjoint of the same unitary operator. And what we have here is the expression A equals U, diagonal form of A times U adjoint. Matrix that's real and symmetric is Hermitian. So is one that's imaginary and anti-symmetric. and in particular, a real symmetric matrix can be diagonalized then by a real unitary matrix, and that's what we call an orthogonal matrix. By the way, we see here two kinds of Hermitian matrices. One kind is that it's real and symmetric, another kind is imaginary anti-symmetric. Don't get the impression that every Hermitian matrix is either real and symmetric or imaginary and anti-symmetric. You can see that's not true if you just write a Hermitian matrix. You take the sum of a real symmetric Hermitian matrix plus an imaginary anti-symmetric Hermitian matrix. You add them together, you have complex matrix that's neither real nor imaginary, and that is neither symmetric nor anti-symmetric. So the space of Hermitian matrices is much larger than the space of real symmetric or imaginary anti-symmetric matrices. So I'm going to skip this example. In fact, I'm going to skip this example also because we do need to, well, we maybe can come back to it. I don't know. Normal matrices. That's an apt adjective because they're the good ones. Normal matrices are matrices that commute with their adjoints. So we have, by the way, this expression, if you haven't had a good course in quantum mechanics, this expression, left bracket, something, comma, something else, right bracket, what's meant, this is called a commutator, and what is meant is the product v dagger minus the product of these things in the opposite order. And so a normal matrix is one that commutes with its adjoint, and so v dagger is equal to v dagger v. And it includes not only Hermitian matrices, which obviously commute with their adjoints, but also unitary matrices, because this commutator is just I minus I, which vanishes. A matrix that can be diagonalized by a unitary transformation clearly commutes with its adjoint, and so is normal. Because if you take v dagger, that's u dagger v u, or I should say u dagger v diagonal u, u dagger v diagonal complex conjugate u. And no matter how you write it, one way or the other, the u dagger cancels on one side, cancels in one term or in the other, cancels in both terms. And you wind up with u dagger, the commutator of v with whoops, there's a typo here. That should be vd in 1.363, so I've got to fix that. This is v diagonal, and these obviously commute because any two diagonal matrices commute, and so you get 0. So to repeat that, if you have a matrix that can be diagonalized by a unitary transformation, then it is a normal matrix. It commutes with its adjoint. On the other hand, we can also show that any normal matrix can be diagonalized by a unitary transformation. And what we do is we realize that since it's a square matrix, it has n eigenvectors with n eigenvalues. So we have n equations like this. Now the square of the norm of this is k v minus vki dagger times v minus vki, like that. On the other hand, since v is normal, we can just move this thing through. We can commute these two terms because they commute. And so we have that this product, that this product also vanishes. And that tells us then that this vector here vanishes. And this vector, when the adjoint acts on the two terms, you get a v dagger and a v star. And that its norm vanishes. What that tells us that k is an eigenvector of v dagger with eigenvalue v star. And if you take the adjoint of that, you have KV is VK. And now, if M is an eigenvector of V with eigenvalue Vm, then from the left with K, we get this expression. On the other hand, using this formula, multiplying by the right, from the right with M, we get this expression here, and subtracting, we have that. And so that tells us very directly that any two eigenvectors of a normal matrix with different eigenvalues are orthogonal. To see that it has n orthogonal, to see that a normal n by n matrix has n orthogonal eigenvectors, we first note that if y is any vector that's orthogonal to any eigenvector, then we have this result here. So the space of vectors orthogonal to an eigenvector of a normal matrix is invariant under the action of the normal matrix. And so following the same argument as before, we find that it has n orthonormal eigenvectors. So what we have finally is that every n by n normal matrix V can be diagonalized by an n by n unitary matrix U, and the kth column looks like this. And it is, so whose kth column is the eigenvector in the basis alpha, right, of the matrix. And we're referring back to this equation. Since these are complete and orthonormal, we can write the identity operator this way and multiply the identity operator by V. We get this expression. And so then we see that if we want to have the function of a normal matrix, well, just f of V is just going to be f of V, f of each eigenvalue times the outer product of the eigenvectors. And of course, that's simpler than the previous formula that was well, anyway, or at least it's a more direct derivation. Anyhow, let's go on then. Let's see, what is this? This is an example. The determinant of a normal matrix, by the way, also satisfies these identities that I mentioned earlier. Compatible normal matrices. Two normal matrices that commute are said to be compatible. So that's just the definition of compatible. And since they're normal, they have complete sets of orthonormal eigenvectors. So if U is an eigenvector of A with eigenvalue Z, then BU is also, because ABU is BAU, which is BZU, which is ZBU. So BU, so A maps BU into ZBU, which says that BU is an eigenvector of A with eigenvalue Z. We know that we can write any normal matrix in a nice diagonal form as a sum of its eigenvalues and outer products of its eigenvectors. Suppose B is another normal matrix in the same space, that A and B are compatible, that is to say they commute. So if you then take the matrix element of their vanishing commutator, what you get is this expression here, and that tells us that that the matrix B vanishes unless unless AL is equal to AK. So if the eigenvalues of A are non-degenerate, then the operator B, any operator that is compatible with it, is diagonal. Consequently, they're both diagonal in the same basis, and for that reason, they obviously are compatible. Anyway, we can write B then in terms of the eigenvalues of A like this, and it gives us this, but these things are diagonal, and so this is actually just well, it's a number, but it's, well, in fact, I have used the diagonalization because the L is the same on both sides. And B maps any eigenket of A into the same eigenket. And consequently, each eigenvector of A is an eigenvector of B with that eigenvalue. And so two compatible normal matrices can be simultaneously diagonalized if one of them has non-degenerate eigenvalues. So this is used all the time in physics. And for example, again, to look at angular momentum, L squared and LZ commute. And so we can simultaneously diagonalize L squared and LZ. And if we, if the Hamiltonian has rotational symmetry, then the Hamiltonian and L, and therefore L squared, they all commute, they're all compatible, and we can make the Hamiltonian the square of the angular momentum and the Z component, or equivalently the X component, whatever, of the angular momentum. We can make them all, we can diagonalize all of them simultaneously, and so they're all compatible. We can diagonalize them simultaneously. If A's eigenvalues are degenerate, then each one may have DL orthogonal eigenvectors. And each eigenvalue has a D sub L orthogonal eigenvectors. In this case, the matrix elements AL, K, B, AM, K prime are 0 unless AL is equal to AM, but if we set M equal to L, then we have a matrix that's DL by DL. And so so if two operators or two matrices are compatible, then in the basis in which one of them is diagonal, the other one will always be in block diagonal form, which is to say it just is instead of having numbers on the main diagonal and zeros everywhere else, it has a sort of avenue of diagonals, and on that thing there are chunks. So if I were able to draw, I could show you what it is, but maybe I can use this. In other words, it looks like this, and then down here we have another one, and then down here we have another one. It looks like that. So what we can do, though, is we can find linear combinations of the degenerate eigenvectors that are orthonormal eigenvectors of both linear operators, so we can simultaneously diagonalize any two compatible operators. And the converse is also true if two operators can be simultaneously diagonalized in the cube. Well, that's kind of obvious. In quantum mechanics, compatible Hermitian operators represent physical observables that can be measured simultaneously to arbitrary precision in principle. And a set of compatible Hermitian operators is said to be complete if to every set of eigenvalues there's a unique eigenvector. There's only one eigenvector. All right, let's skip some of these examples so that we get, is that an example or, yeah, all right. So that's an example of density operators. I'm happy to talk about them, but I think we need to get to the singular value decomposition. So let's go through this. It's actually pretty simple, and I keep thinking that I need to make it even simpler. But anyway, the singular value decomposition, and of course the MATLAB command is SVA, and then parenthesis the symbol representing the matrix, close parenthesis. Every m by n rectangular matrix A is the product of an m by n unitary matrix U, an m by n rectangular matrix sigma. And this nice rectangular matrix sigma is 0 except on its main diagonal. And if m and n are not equal, then that main diagonal runs into either the right edge of the matrix or the bottom edge of the matrix. But that's okay. It's an m by n matrix and it's 0 on them except for the main diagonal, and that main diagonal consists of non-negative numbers. And then the final thing is an n by n unitary matrix V dagger. So we write it this way. The dagger there is conventional. It could have been U sigma V, and then we just be, or we could have had U sigma W, where W was equal to V dagger. In terms of matrix elements, its AIK is a sum on L of UIL, SL, V dagger LK. Notice how enormous you have, notice how much this simplifies things. Because you see, in general, if we wrote A as the product of 3 matrices, we would have IL, LK, and then K prime. So we'd have 2 sums over L and K. Whereas here we just have 1 sum over L, and we just go over, L goes up to the minimum of the 2 integers m and n. All right, so how do we think about this? Basically, it's that we can think of A as in general as a linear operator that maps vectors in an n-dimensional vector space Vn into vectors in an m-dimensional vector space Vm. And it could be that n is bigger than m, or that m is bigger than n. And let me just, right, okay, that's good. Now, each of these vector space, okay, hold on, there's something. Okay, somebody wanted me to clarify something here. What I said here was that if the key point is that sigma is diagonal if it's square, or it's as diagonal as it can be if it's not square, that is to say if m and n are different. And we would have had to sum over a second index here if S were not square. I'm representing sigma in terms of its singular values, which I'm calling S sub L. To go on here, the idea is that A maps vectors in one vector space into vectors in another vector space. And in each vector space, we have infinitely many choices for the basis, the orthonormal basis that we use. For example, we can write the identity operator in the space Vn as an outer product of n orthonormal vectors. But any old set of n orthonormal vectors, and there are infinitely many such sets. And similarly, the target space Vm, that can be, that has infinitely many bases, and we can write the identity operator in terms of outer products of the orthonormal vectors in each basis like this. And there are infinitely many ways of doing this. And if we multiply them, we use these two together, we can say A is clearly Im A In, and that's this expression here. And what you see here sort of says again what I said earlier, namely that in general, A is a double sum. And what's special about the singular value decomposition is we reduce it to a single sum. And so the singular value decomposition of the linear operator A is a choice of two special bases, the A's and the B's, that make this this matrix element diagonal or quasi-diagonal. Because again, there are different, the number of vectors here and here may be different. And in that way, we can write A as kets for vectors in the target space, bras for vectors in the, I guess this one, these are kets in the range and bras in the domain, and then singular values. So it's a very nice expression, and it's completely general. Any cockeyed complex matrix, as long as it's rectangular, can be written this way. And every matrix is rectangular. So every matrix can be written this way. Every matrix has a singular value decomposition. The kets of the special basis for the domain are the eigenstates of the Hermitian operator AA dagger. So in other words, AA dagger, or A dagger A, I should say. A dagger A is Hermitian, so it has n orthonormal eigenvectors, and we have this eigenvalue equation. These are orthogonal because A dagger A is Hermitian. We normalize them, and then the eigenvector EJ is then the squared length of the vector AJ, and so is positive or zero. I have used the letter A to represent too many different things. I once, when I was an undergraduate, took a linear algebra course and an abstract algebra course, and I constructed a proof and used the letter A for 4 different things. The proof was correct. I got a 0 on that problem. Anyway, to get back to this, these vectors AJ are eigenvectors of A dagger A. And they're orthogonal, of course, and E is the squared length of this, and they're positive. The singular values are the square roots of the EJ. Okay, so we've just now figured out half of the, or more than half of the singular value decomposition. For each positive value of Sj, each positive singular value, we just define the special ket in the range as the image of the special ket in the domain under the linear operator A, and we divide by Sj, which is square root of Ej. And these non-zero special kets are, but yeah, for Sj equals 0, the value, the ket Bj vanishes. The non-zero ones are orthonormal because they're in a product as 1 over SKSJ. This in a product. This is an eigenvector of that with eigenvalue Ej. These are orthonormal. We then have this, and that's just delta Kj because Ej, Sj is the square root of Ej. And so these guys are orthonormal. The number of positive singular values is at most n, because we are starting with the, and now I've lost track of which one is n. Yeah, we started with each vector, basis vector in the domain space, and that was n-dimensional, so we can only have n of them. It's also at most m because each non-zero ket is an orthonormal vector in Vm, which only has m dimensions. So the number of positive singular values is most that, the smaller of m and n. And so the singular value decomposition then is A on the identity operator in the domain, which is this, I don't know why I wrote these as separate equations. Anyway, this A on AJ is SJ. Remember, A on AJ is SJ BJ. And so there it is. It's just instantaneous. That's the singular value decomposition. You see it's completely general. Okay, so I'm glad to have done that. By the way, I was once at a conference where in Santa Fe where Cleve Moeller was, the inventor of MATLAB, was present, and he was treated like a rock star by the participants because many of them were biologists and they were just lost without MATLAB. And so I told him I had written this book, and he came up to me very aggressively and said, did you include this, did you do the singular value decomposition? And I said, yes. And I think he was surprised because singular value decompositions aren't that common in physics departments, but they should be. Anyway, in terms of any two bases, the K's for the range space and the L's for the domain space, we can write the identity operators like this. Then the singular value decomposition, well, it's more complicated because you have A like that. But now you use the singular value decomposition of A as the sum on J of ket Bj, singular value Sj, bra Aj. Take all the inner products and you get this structure here. Well, this thing is the matrix element of U. This thing is the matrix element of V dagger. And this is the matrix element of sigma, which is diagonal. And so the fact that UKI is KBI, that's kind of obvious. And this one is sort of obvious as well, that sigma ij is Sj delta ij. What's a little bit more puzzling is that the JL matrix element of the n by n unitary matrix V dagger is, of course, V dagger JL, that's AJL. And so we have this thing is the complex conjugate of VLJ, and is equal to that. And if we now complex conjugate both sides, we get VLJ is AJL star, and that, of course, is L AJ. So this thing makes a lot of sense, namely that VLJ is the special ket in the domain space in a product with a particular vector, with any old vector representing an orthonormal basis in the domain space. Okay. The vectors Bj and Aj are called the left and right singular vectors. And what I should really show here is that the singular value decomposition tells us that the left singular vectors, Bj, are the eigenvectors of A dagger. And that's because using the singular value decomposition of A, we can see that A dagger is this times that. The orthogonality pops down to this. And so you can see that the diagonal form of A dagger is just the special vectors of the range space, the Bj's, and of course also the right singular vectors are the eigenvectors of A dagger A, and they're in the domain space. The kets whose singular values vanish, they are the null space or kernel of the linear operator A. Okay, so I'm going to skip these examples, but I say we can do them on Wednesday. The single value decomposition is a nice way of solving linear systems. If you have AX equals Y, then writing A as it's in terms of its singular value decomposition, we get this expression. And now taking the inner product with Bj, we get that the singular value, the singular value Sj times the inner product Aj with X equals Bj with Y. Well, this tells us, as long as Sj is non-zero, this tells us what the solution is, because the original equation was Ax equals Y, and so the unknowns are Ajx. Well, Ajx is just the inner product of Bj with Y. So as long as you know the left and right singular value, God, I wish someone would explain to me how to use a mouse, because it keeps jumping on me. I guess I need a cat. Anyway, so this gives us the solution. And in fact, if all the Sj's are positive, we can just write the solution in this way. But it's not always possible, because if there are more equations than unknowns, then of course you can't do it. And it could be that there are fewer equations than unknowns, in which case the problem, the solutions are not unique. Okay, this is discussed in some of these examples, but I think I'm going to skip that. This comes to the idea of, we're now at the idea of the Moore-Penrose pseudo-inverses. And let's just, we can just use the singular value decomposition of an arbitrary non-square or square matrix like that. The Moore-Penrose pseudo-inverse is always defined, and it's A plus, and it's V sigma plus U dagger. Now, what is sigma plus? Sigma plus is the transpose of the matrix sigma with every non-zero entry replaced by its inverse. You leave the zeros alone, of course. You don't want a lot of infinities. And so it's a very simple procedure. You can show that it satisfies all these nice identities. So it kind of is like, A plus is sort of like the inverse of the matrix A. It's the best you can do. And the mathematician, English mathematician Roger Penrose is still alive, but Moore was, of course, born an awful long time ago during the Civil War. So I think that's enough for the Moore-Penrose business. So let me go on. If you want to talk about this on Wednesday, that's fine. Let me go on to tensor products. So tensor products describe composite systems, spins of two electrons, or once again, the energy levels and the angular momentum properties of just the non-relativistic hydrogen atom, or just in general, any two, if you have a physical system and you can think of it as, if it's convenient to think of it as having two different parts, then what you might do is you might describe one part by, A might be a physical operator for one part of the system and B a physical operator for another part of the system. They can have different dimensions. The tensor product is of the matrices that represent these physical operators in given bases. The matrix is this funny double super matrix, and it's C IKJL is A IJ BKL, and so the super matrix W looks like this, and acting on any vector VJL acts like this, and so you have AIJ BKL on VJL. So it makes sense. The tensor product operator is a product of two operators that act on two different vector spaces. A acts on kets I and B on kets K, then it looks, A and B look like this, and the tensor product looks like that. Now, what we'll normally do, this is a very formal notation. We'll use a simpler notation in a moment. In fact, this is the simpler notation. And so an arbitrary vector in the space is of this form. Namely, it's a linear combination with arbitrary coefficients of the direct product of two vectors, one in the space S and one in the space T. And sometimes, so this is the general form. There's a special form. The special form is if you can write the vector not as if you can write the vector as the direct product of two vectors that are each in one space and the other space. So this is the direct product of two vectors. And so the sum, if then, is phi I chi k I k. Such a vector is said to be separable. The more general case is that instead of this I k psi being the product of two complex numbers, this is a general thing which depends upon both I and k. So there are n squared different, or n times m different, completely independent coefficients there. Whereas here, you really only have n plus m coefficients. You have the n phi i's and the m chi k's. And so these ones, in other words, the general case, these are entangled if they're not separable. So it's one of these funny ways in which separable is easy to define, and entangled just means not separable. Most states in a tensor product space then are entangled. And if we have D looking like that, then, all right, I'm a little bit confused as to what this is. The tensor product maps an arbitrary vector like that, right? And okay, so the direct product operators are, just trying to see, is this actually simpler? All right, let me skip that for now. Here's a nice example of the hydrogen atom. I think we should go through that on Wednesday if you want, but you may already know that. Entangled states, here are some examples on that. Density operators, well, oh my gosh, we're over time. Okay, let me end class. I don't see any point in going over in class. Is there a last minute question? Does anybody have a last minute question? I tell you what, I'm going to stop recording.